Okay, I guess we'll go ahead and get started.
Okay,
So we have Houcine back again, giving the final installment in the series on Jack characters.
thank you, Jim. I will start by recalling actually the main theorem of the last the five previous lectures. So we had this generating series of k-layered maps, and we proved that for some statistics of non-orientability eta, the generating series of k-layered maps. So in this series, we first control the face type of maps. So we have this variables pi's in which we put the degrees of faces, and also we have this weight of non-orientability. So if the map is orientable, eta of m will be 0, and it is strictly positive if m is not orientable. And then we have this third weight in which we control the number of white vertices in each layer. And using some differential operators, these operators b infinity or bn, we proved that we can construct this series using the operators layer by layer. So we have this differential formula. And basically what it's saying that we can obtain the generating series of k-layered maps by applying first some operators which depend on this variable sk. So we first add the layer k of the map, and then we go on, and the last layer added is the layer 1. So basically the operator bn is the operator which adds a black vertex of degree n, and when specialized in minus alpha si, we are associating to each new white vertex, we are adding the weight minus alpha si. So this explains the weights which appear in the generating series here. And the main theorem of the paper is that this generating series of layered maps, when specialized at lambda i's, the sizes of the part sizes of a partition lambda, this gives exactly the series of Jack characters. So this is the sum over all mu of p mu multiplied by theta mu of lambda, where theta mu is the Jack character associated to the partition mu. And the way the proof works is that we have this characterization theorem of Jack characters, which defines Jack characters as a unique family of shifted symmetric functions which satisfy some properties. So first we had the top homogeneous part property, and then a vanishing property, and the third property was this shifted symmetry property. And actually, the purpose of the last 3 lectures was to prove these 3 properties. And Maciek last time he proved that this series is actually shifted symmetric in the lambda i's. And using the characterization theory, we proved that the generating series of maps coincide with the series of characters. And what I will try to explain today, how to use this formula to prove that to prove positivity in Lassalle's conjecture. So I will start by recalling this conjecture. And then I will, because we already had integrality using Łukasiewicz paths, so I will prove positivity in this conjecture, and then in the second part of the lecture, I will try to give another application of this main theorem, which gives a creation formula for Jack polynomials by adding the rows of the partition lambda one by one. So let me start by this positivity in Lassalle's conjecture. So whenever we have a partition lambda, we can, instead of writing it just using the sizes of the parts of lambda, we can decompose it into regions. And then we associate to each region its length, which is given by this alphabet si's, and the heights given by the alphabet ri's. And conversely, when we have 2 alphabets of integers, ri's and si's, let's say, for example, that we have from r1 to rk, and then from s1 to sk, and the si's is a non-increasing sequence. So you can associate to these 2 sequences, to these 2 integer sequences, a partition given by which has this form. And the idea of Lassalle is to consider Jack characters not in the parts of lambda, but we consider them through these multi-rectangular coordinates. So whenever we have 2 alphabet s and r, we define the Jack character theta mu, so we add a tilde here. So this is defined as the usual Jack character theta mu specialized in this partition lambda, which is associated to the two sequences S and R. And the conjecture of Lassalle says that if we take this Jack character in the multi-rectangular coordinates and we properly normalize it, so multiply by this mu and this sum sign, so what we obtain is actually polynomial in the parameters b minus si's and ri's, and this polynomial also have non-negative integer coefficients. So this was Lassalle's conjecture that Maciek explained in the first lecture, and then what we proved. So
Right.
what
I have a
Maciek
question.
proved. Yes,
Can I ask a question?
of course.
In the last,
Yes.
in here, this is a full conjecture. Now, what if you consider only partitions with distinct parts, which means all the R's are one? Is it easier to prove?
Actually, when we have exactly, so all the Ri's are one. So
Yeah.
what we have here is, in some sense, the theta mu tilde will coincide with theta mu, because the alphabet SI will correspond to this alphabet lambda I of the parts of partition lambda, and this would correspond exactly to this formula.
Mhm.
So it's not. So the answer, it's not easier to prove, but once we have this formula, this corresponds exactly to this conjecture where all the Ri's are one. So even in this case, the conjecture was not known. What was known, however, is the case where we have rectangular partitions. So these two alphabet Ri's and Si's have just length 1. So here we have a partition of length S and height R, and we consider Jack characters in rectangular partitions. And in this case, actually, it's easier to prove because this is actually the case of one-layered maps. So we don't have these problems of layers and of labeling edges each time you are adding a new vertex. So
Thank you.
thank you for your question.
Sorry. And since you are already answering one question, maybe I can ask another one.
Yes, please.
Okay. So first, with this multi-rectangular coordinate decomposition, it's not unique, but there's
Yes.
some statement that this if, for example, two of the SIs are equal, then it just depends on R1 plus Ri plus 1 or something.
Exactly. Yes.
And so this is true for all shifted symmetric functions thought of as functions on partitions.
I think that we need some extra properties of this function so that we can. Well, I'm not sure about that. I'm not sure if we take any shifted symmetric function, we can define something like this. I'm not completely sure.
But the Jack characters are a linear basis.
Yes. So if this is true for Jack characters, this should be true for any.
Okay.
Yes.
This
Yes,
is some.
exactly. So for Jack characters, we will see this using the combinatorial formula.
Mhm. So yeah, I was wondering if you had a direct proof of this, but I guess not, because you kind of didn't think about it yet. So
Yeah, I think that there is a paper by Ferré and Jean-Christophe Novelli in which they consider these properties of shifted symmetric function, but I am not sure what is the exact statement whether all shifted symmetric functions satisfy these properties.
but a posteriori, that is correct, yes?
Sorry? Yes.
A posteriori, it is correct.
Yes. So here actually with some elementary combinatorial properties, we can see that it's correct. Yes.
Okay.
Yes. Thank you. So we had this integrality using Łukasiewicz paths, and now we'll try to use the combinatorial formula that we had for the Jack characters to prove the positivity part. So just from the definitions of these Jack characters in the alphabet S and R, So what we know, let's assume that S is just an alphabet of K parts. And that the SI the S alphabet is a non-increasing sequence. So what we know is that from the definition is that this is exactly the Jack character in which we put R1 S1s and then R2 S2 and so on until, sorry. This is RK times. So from the we know from the formula, this differential construction that we had for characters, that this is equal to t to the power the size of mu p indexed by mu of this exponential of b infinity of minus alpha s1 applied on 1. But now, what since we take we took R1 S1, so we have here to the power R1 and here to the power RK. And here, so B infinity here, few. So this is actually depends on this parameter T, the variables P and the variable U, and this is the sum minus T to the power N divided by N. Put these Ri's in the argument of the exponential here. And all this applied to 1. So now what you want to prove is that is this, okay, so I think that there is a missing. Okay, it's okay. So what you want to prove is this positivity property. And here there are two options. We can actually check that these operators Bn are positive in, so this operator B alpha U is positive in the variable U once we have multiplied by -1 to the power n. So we can check using the differential definition of these operators that everything is positive, and actually it's a polynomial in the SIs and it's also a polynomial in the RIs because they just appear as here in the argument of the exponentials. But you can also give a combinatorial interpretation of these Jack characters in the multi-rectangular coordinates. So to obtain this combinatorial interpretation, recall that we have an interpretation for this operator Bn of P and U. So this operator, it acts on some weights of maps. By adding a black vertex of degree n and possibly new white vertices. And with the condition that we add with the weight equal to U for each new white vertex. So this is how we obtained this combinatorial interpretation of the characters the first time. But now the only difference that we had with the with this construction of characters in the multi-rectangular coordinates is that we have these Ri's and the exponentials. And we can just give a combinatorial interpretation of this by saying that, so this operator B infinity, the way it is defined, so it's the sum of Bn's. And so we just pick a positive integer n and we add a black vertex of degree n. And what we are doing here is that each time you apply B infinity, let's say in layer 1, for example, we multiply by A1. So this corresponds to the fact that we are, in addition to the fact of controlling the white vertices we are adding in each layer, we are also controlling black vertices we are adding in each layer. So what we, so let me just give a
question again. Sorry.
Yes.
Can you scroll up?
Yes.
Yeah. So are you saying that you're gonna prove that in B infinity, it's not just B infinity itself, it is positive component-wise, piecewise. What I mean is, it's an infinite sum, right?
Yes.
Okay. So you're saying that you plan to show that individually minus t to the n over n times bn is positive?
Yes.
Or
so,
the sum?
So actually, the sum is infinite, but at the end, we are taking some coefficient. So since here we are taking a coefficient of p indexed by mu, so mu is finite. So all the sums which implicitly appear in this p infinity should be also finite. So we don't have infinite sums once we have taken these extractions. So we can prove that each bn is positive in some sense, and then we are just taking the sum of bn's, and it also should be positive. But moreover, we can just give a closed formula, a closed combinatorial formula of these characters in the multi-rectangular coordinates exactly in the same way that we had a formula for the characters in the parts of lambda. And this is what I am trying to explain.
Okay, I'll wait. Thank you.
So just to give some intuition about these operators Bn, that so let's assume that we have some map M, and when we apply an operator Bn, we are adding some black vertex V. So this black vertex uses possibly new white vertices, but it also can be connected to some old white vertices of the map M. And then we can make many possibilities like here. And for example, if here I added 3 white vertices, so we have a weight of the form u to the power 3, because it just it depends on this argument u here. So we just use the same combinatorial interpretation, but we add these ri's in the arguments of the exponential to say that each time you are adding a black vertex, we multiply by some ri if we are working in layer I. So we start by adding layer k, we add some black vertices in layer k, and if you added, for example, I black vertices, so this we will have, in addition to the weights of white vertices, we will have the weight rk to the power I. And exactly from this, what we can deduce is that the theta mu in the multi-rectangular coordinates, so this is a sum over, so there is some sign, and then this is a sum over maps, which are layered, and then we have some weights. So we have first, sorry, we don't have this face weight because you already took the coefficient of p mu in the generating series. So this map should be face type mu. And then we have the non-rentability weight, b to the power eta of m. And then we have some normalization here. So this was exactly the formula that we had for the characters, but now we have these extra variables ri's. So if all the ri's are 1, as you said in your question, so this is we obtain the same formula. But now since we have added these ri's, so here we control in each layer I the number of black vertices uses. So this would be ri to the power of the number of black vertices in layer I of the map. Is it clear in this formula? So we had exactly the same formula. So we are summing over maps of phase type mu. We have this non-rentability weight, some normalization, and then for each layer, we control the number of white vertices and the number of black vertices using these variables si's and ri's. And again here, a priori, we have the sum over all layered maps. We have an infinite product. But since we are working only with maps of phase type mu, so the map has a finite size, we cannot have infinite maps. And this product should necessarily be finite. So does this answer your question? Okay, so now what we want to prove is that this is actually polynomial in the variables b, si's, and ri's, and it is positive when we put the minus in front of the si's. So this is what we want to prove, that this theta mu of s and r so we have minuses with si's, and these have positive coefficients. So why is this true? So it's clear that this is polynomial in B, polynomial in the si's and the ri's, except that it's not a polynomial in B a priori because we have this alpha in the denominator. But what happens is that the alpha in the denominator is compensated by the alpha in the numerator. And this is true because for each map, the number of white vertices is at least the number of connected components, because we are working with bipartite maps, and in a bipartite map, each connected component should have at least one white vertex. So we have this inequality here, and using this inequality, we can prove that actually we have this can be compensated. So we are left with maybe some alpha in the numerator, and so this is and we have the b here. So this should be positive in B, and we just put the minuses with the si's, and it's also positive in the ri's. And
So Houcine, was B alpha plus 1?
yes, thank you. So B is alpha minus 1.
Oh, because you may have a power of alpha in this thing.
Yes.
That's
So
actually not positive in the B.
So alpha is B plus 1.
Oh, alpha's B plus
B plus
1.
1. Yes.
That's so it is positive in B.
Yes.
Okay.
So it's not necessarily positive in alpha, but it is positive in B.
Yeah. Okay.
So this shift that has been introduced by Goulden and Jackson, and it turns out that all these quantities are not necessarily positive in alpha, but they are positive in B. And however, we cannot see the integrality from this formula. So because we have these denominators here, these coefficients, which we do not fully understand. So there are some symmetries that should be compensated, but we cannot really understand them because we have this non-rentability weight. But integrality is not a problem because we had it using this different approach using Nasarov's Scaling operators and Tukachevich paths, and this is what Maciek explained in the second lecture. So this finishes the proof of Lassalle's conjecture, the positivity part, and that's all the conjecture. So do you have any questions? So I just would like to go back to this question about that the evaluation of this theta mu tilde in the multi-rectangular coordinates. If we take two representations of the same partition lambda, so we should obtain the same quantity. So this is somehow well defined. And the reason is that whenever we have, for example, some SIs which are 0, we can prove that, whenever we have RIs which are 0, so this corresponds to rectangles with height 0, so they should not appear. We can just forget them. We forget the associated RIs in the associated exponential here. And when we have two, for example, we can add, if we have S2 here and S3, which is equal to S2, so we can just mix them. So we can change instead of having two exponentials, we can have one exponential, and using an argument, an induction argument like this, we can prove that this actually does not depend on the representation of the partition lambda. So now in this the second part, I will try to talk about another application of this combinatorial formula, which gives a creation formula for Jack polynomials. So let's say that let's assume that we have a partition lambda with length L, for example. So what we can prove is that the Jack polynomial J lambda can be constructed using some differential operators. And these differential operators add the rows of lambda one by one. So the last row adds the row lambda 1, and the first row adds the row lambda L. So we start from 1, the constant symmetric function 1. We apply some operators, and each time we apply an operator, we're adding a row, starting from the smallest row to the biggest row. And what are these differential operators? So this Bn plus, so this is the coefficient of t to the power n.
Question?
Yes.
So is this reversible? Do you have annihilation operators? You have a creation formula.
Yes, I think so, yes. So I think that if you take the dual of this, it should be an annihilation operator. I'm not completely sure, but if you take the dual in the sense of the Jack scalar product, it should be an annihilation operator.
Okay.
So in the sense that when you apply it, when you apply some operator on the Jack polynomial, we are just taking out, so we are removing the longest part of lambda. Yes. So this Bn plus operator is the exponential of the sum. So yes, this is. So this is exponential of B infinity in minus alpha n. So this is the same thing as coefficient of t to the power n in the exponential of. Sorry, it should not be an n because we already have an n. So this is the sum over, let's say, k. minus t to the power k divided by k of bk in P and minus alpha n. So what we are doing is that we take the coefficient in T in these operators, which is exactly the integer which appears in the specialization of the operators. So how do we prove this? So what we know is that from the definition of Jack characters, is that the Jack polynomial J lambda is the sum over all partitions mu of the same size of lambda of theta mu specialized in the partition lambda, which depends on the parameter alpha, multiplied by the power sum-symmetric function p mu. And this is actually the coefficient of t to the power lambda, the size of lambda, in the generating series of all maps. So if you take the sum over all partitions nu, for example, of t to the power nu, theta mu of mu, p. And we have a differential construction for this series because it corresponds to the series of layered maps. So more precisely, what we know is that so this is the coefficient of t to the power lambda in these exponentials. So first one b infinity in minus alpha lambda 1. Applied to 1. So, and now we want to extract some coefficient in t. So we will obtain the sum over all ni's, n1, nl, positive. And then we will extract the coefficient of t to the power ni. So these ni's have this, the sum is equal to the size of lambda. And then we extract the coefficient of t to the power n1 in the first exponential. Sorry. And then in the last exponential, we extract the coefficient of t to the power nl. What did I do? Oh, there is a missing b infinity here. Sorry. So it's the exponential of b infinity of minus alpha lambda 1. And this is applied to 1. So what we want to prove now is that the only tuple of ni's which contributes to this sum is the tuple for which n1 ni is equal to lambda I for each I. And for this, it's the same argument that we used in I think the fourth lecture to prove this vanishing condition. So when we take some tuple ni's such that, so this is different from the tuple lambda 1, lambda L, then we know that there exists some I such that ni is bigger than lambda I. And using this annihilation property with this sequence of spaces PSs, we can prove that with exactly the same kind of ideas, we can prove that when we take the coefficient of t to the power ni in the exponential of b infinity in minus alpha lambda i's, and then we continue until nl, applied to 1, so this is 0. And the reason is that this power here of ni is bigger than the power of lambda I, and we have proved that the previous exponential applied on 1 are in some space which is annihilated by such an operator. And if we prove this, so all the tuples ni for which there is some ni different from lambda I, this is 0, and what is left is just the tuple lambda i's. And this gives exactly this gives the proposition. Sorry. That the only tuple which really contributes is this tuple of when the coefficient of each operator corresponds, the power in t in each operator corresponds to the integer which appears in the evaluation of this operator's b infinity. And this allows to add all the rows of lambda 1 by 1. And the formula obtained is nicer than the formula that we have without this vanishing condition techniques. Are there any questions?
I guess maybe this is a little,
Sorry?
I guess I have just a general
Yes.
question. So
Yes.
you have this operator now to generate the jacks. Now, in the stuff with Diodario, do you extend this to the McDonald J-mu?
Yes.
And is that a theorem or a conjecture?
That's a theorem. So for this creation formula is a theorem, and that's a very good transition for my next and final remark about
Okay.
these delta operators. Thank you. So actually, these operators can, it turned out that they're related to this delta operator from which have been first introduced by Bergeron, Garcia, Hyman, and Tesler, and studied in many other works. And the relation is quite simple to state. So we can define, I will give the Jack analog of these operators. So to define these operators, so they depend on some variable u on the space of symmetric functions. So they are defined by their action on Jack polynomials. And we want that their actions on Jack polynomials to be, so they are diagonal on Jack polynomials. So let's say that we act on the space of symmetric functions in this some variables pi's. So these pi's are the power sum symmetric functions. So we have a j lambda, and the action is, so this should be the product over all the cells of lambda of u plus the content of the cell. And this is multiplied by j lambda in P. And if you remember this theorem of Stanley from the second or from the fourth lecture, I think. So this quantity is a Jack polynomial, j lambda, but specialized in the variable u. So let me recall what that this means. So this j lambda of u is the function obtained by, so we start from the Jack polynomial in some expressed in some power sum symmetric functions qi's, for example. And then we replace all the qi's by this variable u. So we send all power sum symmetric functions to one single variable u. And this actually, this can be obtained as a limit from some platistic substitution in the language of McDonald polynomials. So all these have natural generalization to McDonald polynomials. And then,
Sorry, I missed something. What is C alpha?
so sorry, yes. C alpha is the alpha content of the box. So C alpha is I hope that I'm not mistaking the conventions, but we take alpha times the I of the box minus 1 minus j minus 1, where the box has coordinates I and j.
Mhm.
So I is the horizontal coordinate and j is the vertical coordinate.
I see. So if alpha is equal to 1, we get our
Yes, so this is if alpha equal to 1, so we get
content
the visualization
of
for
a
full function.
partition.
So
If
yes,
alpha equal to 1, yeah, you get the
Yes.
classical content.
Exactly. Yes. Yes. So this is the, I think, the hook length, hook content formula.
Right.
Yes. Yes. And this formula, so for the Jack polynomials, I think it has been proved by Stanley in this paper from 89, and it also have a McDonald generalization, and it was given in the McDonald book. So we have this definition of this, delta operators, and the statement is that, so these Bn operators in the variable u, so this is, so we take the multiplication operator by Pn, the power sum symmetric function Pn, and we conjugate it by the operator delta u. And this coincides with the operator Bn. And the proof is that we can make the connection between the two formulas using this tau function. So we have this function tau which depends on the variable t, the variables p and q, and the additional variable u. And this was the sum over all partitions lambda of t to the power lambda, j lambda in the power in the variables p, j lambda in the powers q, and then j lambda in this variable u, so this specialization. And then we divide this by the square norm of Jack polynomials. And the idea is that this function, if you remember these techniques from the fourth lectures, you can understand the operators Bn by their action on this function, because we had this differential equation from the paper of Chapuis and Doenga on the B conjecture. And the interesting fact here is that this function is obtained from the Cauchy corner by applying the operator delta u. So just from the definition of the operator delta u, this is delta u acting on the Cauchy kernel. So this is the series with two alphabets, and we understand it pretty well because we have formulas in the power sum functions or with monomial functions. So now, so this is the first fact, and the second fact is that, so this theorem of Chapuis-Doenga, which says that when we act by the operator Bn in the alphabet P, and which depend on this variable u, on the tau function. So this is the same thing as, maybe I will divide here by n. This is the same thing as the derivative with respect to Qn of this function. So what this equation says is that we can increase the degree in the alphabet P on the function tau. So this is the same thing as decreasing it using this derivation with respect to Qn. And actually, when we use these two formulas and we extract some coefficients, we can prove that Bn has this formula. And actually, now we can do the same thing with these operators, B infinity, for example. You can, because B infinity is just the sum of this, and then you can take an exponential, and we have some natural formulas with these delta operators. And in the paper with Michele, we used these formulas to prove some creation identities on McDonald's side, except that the two proofs are very different, because on the Jack side here we have these combinatorics behind, which is and that's why we understand these operators. So we have these catalytic definitions which uses this additional alphabet y. And on the McDonald side, however, we have other identities. So this five-term relation and identities that we do not have on the Jack side. And the problem in we still have many open questions, because we have operators which that can be used to define McDonald characters, so two-parameter generalization of Jack characters. And we have many positivity conjectures for these characters, but the combinatorial side is still missing. So we don't know if there are some combinatorial objects behind these positivity conjectures or not.
One more question.
Yes, please.
In your proposition,
Yes.
You write Bn as a conjugation of Pn.
Yes.
Now, is this also possible to read the other way? Pn as a conjugation of Bn?
Yes, because this delta U operator is
Invertible.
is invertible, so we can just actually it's a consequence of the Peary rule that, for example, this identity, so this is a polynomial in U, because we divide by delta U, but then we act by Pn, so we are adding some cells if we act on Jack polynomial, and then we remultiply by delta U, so we can use the Peary rule to see that this is a polynomial in U. Of course, in the Jack case, we already knew it, because we have the combinatorial formula for the operators Bn. But for example, in the McDonald case, we don't have a combinatorial formula, so this Peary rule is important. So yes, and these operators they appear quite naturally in the McDonald language, because there are some variants of the theta operators and things like that. And yes, so this is what I wanted to say in this direction. And then just some final comments. So we still have some open problems or open questions related to these operators, because we had these differential operators which allow us to construct generating series of maps. And it turns out that they're also related to these combinatorics of Łukasiewicz paths. And so we understand the connection on the operator level, but we do not understand how the combinatorics are related of maps and Łukasiewicz paths. And then it will be also very interesting to understand how these operators act on the monomial basis, for example, because we were trying to make some tests of how this Pn act on the monomial basis, and they do not seem to be positive in the parameter alpha, for example. However, the Jack polynomial itself should be positive in alpha, because we have these formulas of Knope and Sahi, which say that they have expansions in the tableau. But even in the case alpha equals 1, for example, we do not really know how to relate the combinatorics of maps to the combinatorics of tableau or other objects which appear in the monomial expansions. So I will stop here. Thank you.
Okay. So thank our speaker. And do we have any questions?
Yeah, maybe the one at the bottom where you have the contents. Yeah, the contents formula, that interests me a bit.
Yes.
So there is this classical hook content formula for alpha equal to 1.
Yes.
And then is this extendable for alpha?
So
that is something like this. In the hook content formula, you have U plus C1 of a cell divided by the hook of the cell.
Mhm.
So do you have something like that that is combinatorial in its nature?
So what I know is that in the Jack case, we do not have some we cannot interpret this like as dimensions of spaces. So we don't have the representation theory side of the story. So we have combinatorial this combinatorials formula. So this J lambda of U, we can write it using this combinatorial formula of with alpha contents. But however, we do not have these formulas with dimensions of some spaces. Because when we take alpha equals 1, we can, so this is basically the Schur function up to this product of this hook product. And so we can see the other formula as a specialization of this one. But we don't have the representation theory side. So
Okay. Thank you again.
thank you.
Any other questions?
No, so no more questions, but thank you to you and also to your collaborator for some very nice mathematics and very nice lectures.
Well, thank you very much for questions.
Yeah, you certainly left us with a lot to think about here, to absorb.
Maybe I can just ask, I mean, is it true also for shifted Macdonald polynomials that you have this this kind of independence of expression as a function on lambda for the rectangular decomposition?
So for Macdonald characters,
Yeah.
so you mean yes, so we can define some Macdonald characters using this characterization theorem of so which gives.
So I mean, it seems to be almost some sort of equivalence that shifted symmetry is equivalent to this kind of I don't know, what is it, condensation or something of in rectangular coordinates.
Yes, yes. So I think that this part we can we understand it pretty well because we have these creation formulas. So we can define in an abstract way Macdonald characters as the unique family of shifted symmetric functions, but in the Macdonald version of shifted symmetry. And we satisfy some properties. And
the properties would be the top term is the power sum and the lower terms are vanishing.
Exactly. Yes. Yes. That's exactly it. Except that the shifted symmetry is instead of making
QT symmetry, right?
Yes, there is some definition of it, and when we do this, these characters we just made some tests, and these characters seem to be positive, and we also can construct them using some operators.
Positive means for Q and T between 0 and 1 or something like that.
Not exactly, no. So we should make some reparameterization because already in the
reparameterization.
Yeah, because the Jack polynomials can be obtained from Macdonald polynomials as a limit, but this limit is not that obvious. We should first divide by something. So so before taking to have positivity, we should replace maybe Q by 1 plus T times gamma or say something like that, and then so there is some shifts like in the Jack conjectures, which these shifts already appear in the Jack case, so it's not that surprising. We can also use some operators which are defined in this way to construct these Jack characters. So we have operators, we have the objects, but what is missing?
This positivity for thing that you prove for Jack characters, it's really some positivity statement for shifted power sums, let's call them.
Okay.
Yes. Did you check if the positivity holds for shifted monomials?
Yes. So I know this. There is a paper by Valentin Ferré and Per-Alexanderson in which they define some. So they introduce some positivity conjectures for monomial. Yes, so some monomial version of Jack characters, and they have some positivity conjectures. So I think it's a paper from 2017 or 2018, but it's not exactly in the same sense. I think I'm not completely sure that this positivity conjecture, they involve some factorial basis. So instead of taking the basis of lambda i's, we take the factorial basis of lambda i's.
No, so I'm right. So I don't know which paper of these guys it is.
I think it's called multi-rectangular, I don't know, nominal coefficients of multi-rectangular in multi-rectangular coordinates or something like that.
Ah, okay.
Yes. And the conjecture is still open, and so it's also another mysterious thing for me is that we cannot pass from use these formulas in the power sum basis to get some information in the monomial basis. So of course we can just translate we can pass from power sums to monomials by saying that we are going to decorate the faces of the map. So instead of giving the weight pi to a face of degree I, we will choose some color, some positive color, and we will associate to the face weight xj to the power I for some positive j. But then the formula to obtain is not positive. And we know that jack in the monomial basis are positive. So we don't know how to maybe simplify these formulas.
Yeah, there's certainly a lot to think about.
Yeah.
Very good.
Okay.
Take care.
Yeah. So let's thank our both Houcine and Maciej again.
Yeah.
Very good. And by the way, the next IPAC seminar will be a week from Tuesday. Next week's off, and then George Seelinger of UMichigan will be giving a series of 3 talks on a raising operator for the modified McDonald polynomials. So George is part of this research group with Mark Heyman, Jonah Blasiak, Jennifer Morse, and Anna Poon, who've solved several different open problems in the modified McDonald diagonal harmonics world. And this is their latest raising operator formula, which has been known for Hall-Littlewood polynomials for a long time, but now they have something like that for these modified McDonalds. So it involves the elliptic Hall algebra and in addition to classical generating series combinatorics and bijective question arguments. So that will be neat. And then Anna Poon is giving a few lectures which may involve that same stuff or may involve something different after George. Okay, so anyway, we'll see you all hopefully a week from Tuesday. Thanks again. Bye.
Bye.